Hello, my name is Shreya Puranik, and my project is based on experimenting with image generation using a robust classifier. My implementation is based on the paper Image Synthesis Using a Single Robust Classifier by Shivani Santurkar and others. The main motivation for this project is the fact that the paper uses an adversarial robust classifier for its image synthesis tasks. An adversarial robust classifier is one that can test time perturbations of inputs when faced with an adversarial attack that attempts to confuse or mislead the classifier into misclassifying images. As we can see here, in standard models, the classifier is trained while minimizing the expected loss L over the given data. However, in robust models, the classifier is trained by minimizing the worst case loss over a perturbation set delta, which consists of small imperceptible changes or steps. Another idea proposed in the paper is controlling the input features by performing gradient descent on the model output. So the key concept used is maximizing the predicted class score of each target class using projected gradient descent, PGD, which is a type of gradient descent especially used in constraint optimization problems. Some of the tasks mentioned in the paper are realistic image generation, image-to-image translation, super resolution, and image in painting. For my implementation, I primarily dealt with the image generation and image in painting tasks. For image generation, I introduced varying levels of granular noise present as the grain feature in the code, implemented two different loss functions and compared them with the original, and lastly, implemented different optimization methods in the model. And for the image in painting task, I changed the path size, which is the size of the missing pixels in an image to improve image reconstruction, and also implemented different loss functions. As we can see here, generation loss 1 and generation loss 2 were modified from the original loss, which only consists of the cross entropy loss, but I introduced the negative log likelihood loss and the Poisson negative log likelihood loss in these loss functions. The images generated from my implementation show hyperpigmentation, which you can see in the first two lines, as compared to the original. Moreover, in the second loss function, which is seen in the middle line, we can see that the classifier misclassifies some target classes in the output. So we can see that even though the model is robust, the learning accuracy decreases in this case. Here I changed the constraints to 2, infinite and unconstrained. The paper uses an L2 norm PGD for optimization purposes, basically taking L2 normalized gradient steps, which you can see on the left. Setting the constraint to infinite results in an L infinite normalized PGD, basically saying that we take signed gradient steps. And with unconstrained, the optimization no longer uses PGD and it reduces to a standard gradient descent. So from this, we can observe that keeping the constraint to 2 is actually the best optimization method. In the image in painting task, I introduced a few loss functions and compared them to the original. Here's one of the modified loss functions where I returned the sum of negative log likelihood loss and cross entropy loss as compared to the original setup, which only returns the cross entropy loss. From the images generated, we can see that the modified loss function, the images show hyperpigmentation as you can see in the bottom here. But the target classes are also better inpainted than the original. Because the original, we see that the inpainted area does not necessarily match with the original image, whereas in the modified implementation, while the images do look different and it's not just filling in the missing pixels, the objects seem to stand out more clearly. Based on the results obtained, it can be inferred that increasing the granular noise during the input decreases the quality of the images generated as the output. Moreover, the image diversity is also compromised as we increase the grain value. For example, images belonging to the same class of the dataset start looking like each other with no variations in color, shape, or position of the object, as well as the background in the images. However, with a lower grain value, we see that the images of the same class show diversity in all these attributes. And increasing the path size in image in painting tasks requires more epochs for the model to produce images of higher quality, basically saying that it increases the training time. So yeah, that's mostly it. And I would definitely say that due to the GPU constraints, I had to stick to CIFAR 10, even though the paper uses other large datasets like ImageNet. And the model was also pre-trained using the ResNet 50 architecture, so further work would be retraining the entire classifier on a different architecture like Inception v3 or VGG16 to compare the results.